now we define f2 from x2 to x. Okay, now for each x1 belongs to x1, define f2 x1 from x2 to x by f2 x1 of x2 is equal to x1 x2 a3. Then you can easily verify that this f2 x1 is constant. Then one can easily verify that f2 is f2 x1 is continuous for each x1 belongs to x1. So therefore the composition, f2 x1, it's a composition mapping from x to the interval 0 1 is also continuous, it's from this f2 is from x2, it's from x2 is, it's not intro, it is 2 points at 0 1 with discrete topology, is continuous and hence constant, as x2 is connected, For if it's not constant, then it will be the continuous map from x2 onto this space 0 1. Then that will give this x2 will be disconnected, as we have already proved in the previous lectures for the characterization for the space to be disconnected. Is that there is a continuous function from x2. There is a continuous function from x to the discrete 2-point space 0 1 onto discrete 2-point space 0 1. So since this x2 is connected, it's not disconnected. Therefore, if f2 x1 is a continuous map from x2 to discrete space 0 1, then that map should be constant. So this x2 is disconnected. Now to find the value of f2 x1 at the point, say it's say 8 2. What's that value? That value is x1 a2 a3, x1 a2 a3 for each x1. Its value is x1 a2 a3, and that's equal to, if you can see it, it's equal to f1 of x1, and that we are seeing that this is constant. f1 of x1, it's constant because f1 is a continuous map from x1 to the discrete space 0 1. It's a constant map, and its value is f of a for each x1. Its value is f of a. So that means f2 x1 at a2, it's equal to f of a, which implies its value at every point is f of a. It's equal to f of a for all x2 belongs to x2. For all x2 belongs to x2. So this value is constant, so which implies f2 x1 at x2, it's constant. It's equal to f of a for all x2 belongs to x2. It's equal to f of a. So which implies that f of f2 x1, its value is actually f of what's f2 x2, it's equal to x1 x2 x3. So it's f of x1 x2 x3. That implies f of x1 x2 a3, it's equal to f of a, it's equal to f of a. So that value is f of a. Okay, it's f of a. So next we define f3. We define f3 now. Now we define f3 now for each x1 comma x2, for each x1 belongs to x1, x2 belongs to x2, we define f3. Let me write here x1 x2 from x3 to x by f3 x1 x2 at the point x3 where x3 belongs to x3. Let's define this by, it's equal to say x1 x2 x3. Then this f3 is also continuous. Then f3 x1 x2 is continuous for all x1 belongs to x1, x2 belongs to x2. It's continuous. So that implies the composition f3 x1 x2 from it's a map from x3, because f3 is a map from x3 to x. Then this f is a map from x to the discrete space 0 1 is continuous and hence constant, because x3 is connected and hence constant as x3 is connected space, as x3 is connected. So this map is constant, and we find its value at a3 first. Let us find its value at a3. Now what's its value? f3 x1 x2 at a3. At a3, let's find the value of f3 x1 x2 at a3. It's equal to x1 x2 a3. It's equal to x1 x2 a3, and that x1 x2 a3 x1 x2 a3 x1 x2 a3, it's here you can see f2 x1 x2. Actually this value is you can see it's equal to f2 x1 at x2. You can see that's it, because f2 x1 is equal to x1 comma x2 a3, so it's equal to f of x1 x2 a3, and this is constant. It's equal to f of a, as we have seen this. f2 x1 of x2 is equal to f of a. It's f of a is constant for each x2 and x1. For all x1 belongs to x1, x2 belongs to x2. It's a constant value. So since this f3 x1 x2 it's a constant map, so that means its value at every point is some constant number, but its value at a3 is equal to f of a. So which implies that f of f3 x1 x2 at x3 it's also equal to f of a for all x1 belongs to x1, x2 belongs to x2, x3 belongs to x3. So this implies what's f3 of x1 x2 x3, it's equal to x1 comma x2 x3. It's equal to f of a for all x1 belongs to x1, x2 belongs to x2, x3 belongs to x3. So which implies this f is constant. F is constant, which is a contradiction, because f is a continuous map. So here it's a continuous and constant. It's a contradiction. A as f from x to the discrete space 0 1 is on to is on, so therefore it cannot be constant. But here this f is constant map. Here this f is a constant map. It's a constant map. Its value is either 0 or 1 for each point in the product space X. But this map is constant has already because we have assumed that X is disconnected, therefore this map is onto map. so it cannot be constant by our assumption and contradiction. Therefore we get a contradiction to this our assumption that the map f from x to 0 1 is on 2. So that means f from x to 0 1 space is not on 2, so which implies x is connected. So that means whenever we have three connected spaces x1, x2, x3, then their product is also connected, x equal to x1 cross x2 cross x3. And also we know that R is connected, so that means it is product R cross R cross R cross n times, you can see it's also connected. So Rn is connected space. And similarly you can prove Cn is connected. First you prove C is connected. You see that C is equal to R cross R. It's homeomorphic to R cross R. You first verify this. C is homeomorphic to R cross R. Okay, if you verify this, C is homeomorphic to R cross R. Since R cross R is connected, it's R square, so that means C is also connected. So whenever C is connected, that means C cross n times, which is equal to Cn, is also connected. So that means both Rn and Cn, they are connected spaces.